Today we're going to talk about earthquakes and the destruction that they cause. This is part 2 of the earthquakes lecture series, so if you're looking online on It's Learning, you'll find the quiz that goes right along with this. I think it says Earthquakes Lecture 2. So let's dive in here and discuss a little bit about why do some earthquakes cause a horrendous amount of damage and others don't do quite so much. So there's a lot of factors involved. Obviously, all of it is due to the vibrations of the ground that are caused by the earthquake itself. But the factors that are involved here include things like how intense was the actual earthquake? How intense are the vibrations in the ground? And obviously, greater intensity is going to cause more damage. But also, you have to take into account how long the vibrations occur for. Are they very short? Or do they go on for a really long time? Also, is the material that the vibrations are going through, are they moving through solid rock, or are they moving through soil that has some water in it? Like the results of that will be very, very different. And on top of all of that, we have to think about the human structures that we're talking about getting impacted by these. What kind of structures are they? How are they built? What's their construction? What are they built on top of? All those things come into play to determine sort of just how dangerous any given earthquake is going to be. So let's look first here at the design of the buildings and how well they can withstand an earthquake. By far and large, the biggest factor in building design seems to be kind of like how well reinforced it is. Okay, no matter like if it's a big earthquake or a small earthquake, what we found is that buildings that are built out of stone or bricks that are not reinforced in any way tend to really just fall apart in even some pretty small earthquakes with not that much even intensity of the earthquake. They'll come down real quick. You might want to take a look at your quiz question there because that's the answer. Now, what they're built on also, of course, matters, but if they're built poorly to begin with, you're already in a lot of trouble. So one thing to kind of remember from our talk here, and I know we've mentioned this previously in class, is that if there's an earthquake going on and you happen to find yourself in it, obviously getting out of a building is a great thing to do if you can. But another important fact that you need to remember is that you don't want to be near any stone or brick buildings because those bricks and those stones are going to start ejecting, and if enough of them fall out, whole walls will come down and it won't be long before the entire building is coming down. So getting far away from those structures is a good thing if there's an earthquake going on. Now the next part that I want to talk about, next thing I want to mention, is called liquefaction. Liquefaction is a very bizarre phenomenon. It happens when you've got some like sandy soil type material that's saturated with some water. There has to be some water in it, and as the ground shakes, the soil, which was originally quite solid, you could have buildings built on it, you could be walking on it. Suddenly, it almost turns to like quicksand. It turns to a fluid, like liquid even. And then things that are sitting on its surface, they suddenly sink. Things that are underground that happen to be less dense than things that are above the ground, or less dense than the ground itself, are going to float up to the surface. Now, that's a real strange thing because we've seen situations where objects such as gas tanks that might be buried underground and be empty are filled with air, right? They're less dense than the surrounding soil, so it's almost like releasing a balloon underwater. They just float right up to the top. And if you can think of some other objects that this might occur in, we have had instances where coffins which are sealed will float right up to the surface because of liquefaction of the ground. So the effects can be really drastic and kind of surprising. During a liquefaction event, you'll see buildings like this one right here just subside like into the earth like they've just sunk. So if you look closely, you'll notice that building didn't fall over. The ground like literally ate it. Those people that are standing on the surface there, their feet are at the level of like part of that building. The rest of the building is completely under the ground, and once the shaking stops, the ground sets back up again, and it's hard, so it's like been just re-encased like that. It's a real strange effect. It was a lovely, balmy November day, and the people living in the high-rise were going about their daily lives. Unbeknownst to them, their building was built atop a fault, and the material underneath of it was some loosely unconsolidated, sandy-type subsoil with a lot of groundwater flowing beneath it. Little did they know that that day, that fateful day, the ground beneath their feet would begin shaking. Oh no! And when it stopped, their building would have sunk into the ground. Strange things like gas tanks and even coffins would have floated to the surface, leaving destruction in the wake. This is liquefaction. Another thing that can be caused by earthquakes is a phenomenon known as a tsunami. So you might have heard this called a tidal wave before, and that is kind of an old word for the word tsunami. The reason that tidal wave is not used anymore is because it's really a poor description of what's actually going on. These things have nothing to do with tides. They have nothing to do with the moon's gravitational pull on the Earth or the Earth on the moon. None of that business. A tsunami can be triggered in a number of ways, but earthquakes are the primary reason for this. And what occurs to trigger a tsunami usually is that part of the ocean floor along a fault is either lifted or drops. And when that occurs, you can think of it a lot like if you were sitting in a bathtub and you moved your body rapidly to one end of the tub and then back to the other end of the tub, your body would kind of slosh that water. So the dropping of a big slab of rock in the ocean, or the rising of a big slab of the ocean, rock in the ocean, sets off this sloshing motion that sends out a wave in all directions from that particular location. And if you're out on the open water, you wouldn't even notice. You would not even notice a tsunami. You just bob right up and down like it wasn't a thing at all if you were out in the open ocean. But if you're near shore, where the water starts to get shallower, what happens is the wave actually hits the shoreline. And if we can see, here's a picture. As it hits the shoreline, the bottom of the wave bottoms out, and just like any old regular old wave, the top is going to crest over. Now, in the case of the tsunami, the height of that wave is considerably taller than any other wave that is going to hit the coast. So we're talking about something traveling at maybe 50 kilometers per hour. When it hits the shore and even slows down, these things can lift up really, really high. There's really no escaping a tsunami, and as we watched on the video there, or if you haven't watched it yet, it's pretty horrible. If you're on the beach and you see the water suddenly recede like way out, don't think to yourself, oh, this is really cool, I'm going to go check out those shells and all those things that are suddenly exposed by the water, because if it's a tsunami, that will be the warning. You need to get away real fast, and honestly, there's probably not time to escape, because you're not going to outrun something moving that fast. So when these things hit land, they cause some serious damage if there's anybody on the beach or anywhere near the beach. And then the flood waters just push inland really, really far. So there's other ways that tsunami can form as well, and they can have to do with earthquakes. If an earthquake sets off a landslide in a narrow inlet of a bay, it can also trigger a tsunami from the rocks sliding into the water. So that can cause it too. But the traditional way that they happen is because of the ground getting shifted underneath the ocean and making the water slosh. Now, as you guys saw in the video, we do have a tsunami warning system, and any large earthquake that happens out in the Pacific Ocean, it's reported immediately by those seismic stations, and we try to warn people that are in the path of it to evacuate to higher ground, to prepare for the tsunami making landfall. And these things move fast, so sometimes the warning is not, you don't have a lot of time. You've got to get up and get moving. Now, it's not something we have a lot of experience with here in the middle of the United States in Indiana. We don't have to worry about tsunamis, right? But if you're ever near the coast anywhere, if you're in Hawaii, someplace like that, it is something that they do drills. They do tsunami drills in the same way we might do a tornado drill. What would you do? Well, we'd evacuate out of the building as fast as we could. We'd get to higher ground, that sort of a thing. You definitely don't try and stay in the building that's near the coast if there's a tsunami coming. So some other dangers that we want to look at here, and you'll want to kind of keep note of all these dangers because there's a question about the types, or a few, about the types of dangers that earthquakes can pose. Another one that I've mentioned already is a landslide. Now, these don't have to happen in the water. They can actually happen on a mountainside that happens to be above some land. And this is really pretty common out in California because you've got a lot of earthquakes along the San Andreas Fault, and you have a lot of buildings built right up against the Sierra Nevadas, and ground can just slide away. I know a lot of folks think, oh, well, landslide, why don't you just kind of walk away from that, or just run away, or maybe climb up on top of your roof, kind of get away from that sort of thing. Landslides are fast things, and if you got caught in one, and the liquidy muck that is formed from these things, it will wipe you out. Let's just take a look at this picture, and we'll come back here to finish talking about this, but you almost can't tell which way is up in that picture, can you? When you look at that, it is just absolute wreckage. Those are bits and pieces of houses. There might be some cars in there. There's trees pointing every which direction. You can see the slope of the land off there to the right a little bit. When mud slides down these things, usually what occurs during a landslide is that you do have some wet soil along that mountain slope. Maybe there's some snow up there that's melting, something like that, and when the shaking occurs, it might start to liquefy a little bit like we discussed. And if that's on a slope, all that material is coming down, and it can be literally like concrete, like just flowing thick stuff. You couldn't swim in it, you couldn't move in it, you're just going to be trapped and swept away, and all the bits and pieces are going to be everywhere. And then as soon as it stops flowing, just like other liquefaction type events, it hardens right back up again. So it's real dangerous stuff, a landslide. It's nothing to think is a simple ordeal. Now, another thing that occurs pretty often in an earthquake is outbreaks of fire. And it might seem strange, but if you think about what we've done underneath the Earth's surface, is we've run all of our electrical lines, and we've also run all of our gas lines. Now, when the Earth starts shaking, those gas lines will break and start venting gas, right? And if you have electrical sparks going on while there's gas leaking, you have a very serious fire. In the famous earthquake in San Francisco, the earthquake of 1906, where there was just so much destruction, most of that destruction wasn't the shaking as much as it was the fires that it let loose. And if you look at the pictures of this thing, I mean, there are streets and roads that are just heaved upside down, and cars on an angle and in holes. Like, it damaged the heck out of this place. But really, the majority of the damage was the fire that just burned the entire city. So landslides, fires, tsunami. What else did we mention there? I think that's the majority of it so far that earthquakes cause. So let's talk now about earthquake predictions. So as far as predicting an earthquake actually occurring in any given area, to be honest, scientists are at pretty much a complete and total loss. Short-range predictions, like up to days, weeks, we're no good at that. Long-range predictions, like out to years and things like that, we've really not been successful there either. And it's not due to really a lack of understanding of how earthquakes work. A lot of it just has to do with the fact that they are pretty unpredictable. We can look at things like the seismic gap, which is an area along a fault where there's not been earthquake activity for a long period of time. And we can do things like say, okay, there's a large gap of time here along this fault where there hasn't been a big earthquake or any earthquake activity. And we know traditionally in the past that, X amount of time usually passes and there's another big earthquake. So we can kind of make a prediction in that sense of, we might be overdue for a big one, but really how big or exactly when, there's really no good way of doing that. So earthquake warning systems, if we set off a warning, I mean, we're talking seconds. Like there's like hardly any time to take cover or do anything. Like it's one of the very difficult things for us to predict. So a lot of earthquakes, they happen along known faults and known boundaries, so we know where they are and where they'll occur. That part's really not surprising. And using this seismic gap sort of concept, we can kind of make a little bit of a prediction about maybe how bad the next one's going to be in any given area. Because if a fault has a lot of little earthquakes along it, a lot of small slippages, we know that it's releasing its energy in less destructive, like more often small quakes. But if there's nothing that's occurring for a long period of time, we know it's really bound up and it's building up a lot of tension. And when it finally lets loose, it could be a real big bad one. So in some sense, we can know a little bit. But yeah, the truth is we can't really make predictions on earthquakes. We just don't know a way to do that. I'll demonstrate to you motion along a strike-slip fault boundary here. So this is sort of what might occur, say, in the San Andreas fault, where you've got a transform fault where there's material sliding past other material, and as it gets caught, it will build up pressure, build up tension, and then those rocks will suddenly release and deform and shift, and then that's what sends out the earthquake event. So you can kind of think of the sandpaper that I've got here as one of the sides of the fault, and the brick here as the other side of the fault, as it's creating friction along the fault line where it's trying to slide. So as I increase the tension here, I'm going to start winding up the string, and you'll notice that you can tell this brick is coming under tension. Like it wants to move this direction, but it can't because there's too much friction with the other plate beneath it. Now, as that builds up, eventually there's going to be a point where it's going to release. Now, that's incredibly difficult to predict when that's going to really occur, right? But we know it's going to happen because the pressure is still building and building and building. The tension's building up, and then eventually it's going to be more than it can handle and it's going to slip. Now, it might slip just a tiny little bit like this, or it could slip a whole bunch, right? And what's the difference? Well, the difference is that when it slips a little bit, it can keep slipping a little bit and relieve that tension, right? But what happens if it gets stuck, like it really gets stuck? Well, as the pressure builds and builds and the tension builds and builds and builds, and you don't get any little earthquakes for a very, very long time, when it finally does release, it's going to be more catastrophic. More energy is pent up, more energy is going to be released, and it's a bigger quake. So kind of simulates for you some of the typical pattern we see, like in the San Andreas, is that there's lots of little quakes that tend to release the pressure, but if it ever starts to get built up and we know that it's not releasing, we can start to predict, hey, there could be a bigger earthquake on the way. Now, pinning that down to a day, an hour, a month, a year is next to impossible, right? But we can at least kind of get a picture of how much energy is built up in that situation. So let's look at how we know what the Earth's interior looks like, which also relates to earthquakes. We actually know what's inside of our planet, not because we have drilled down to the core or even the mantle. Heck, we haven't even drilled through the crust all the way. Like that's and it's not that thick. It's just a long way to go, and it's very difficult to drill that far and very expensive. So when you think about all the oil drilling and things like that we do, we really haven't drilled very far. So our Earth consists of three major zones that we define based on their composition. And they are known as the crust, the mantle, and the core in order. So we'll start with the crust here. The crust is this thin, rocky outer layer, and it includes the stuff that the oceans are sitting on as well. They're sitting on top of crust as well, and it varies in thickness quite a bit. Underneath the oceans, it's only about 7 kilometers thick, so the thinnest crust is under the oceans. The continental crusts can be much, much thicker, like 8 to 40 kilometers. And if we're talking about mountains, it's extremely thick there, 70 kilometers thick even in the mountainous regions. So the crust is kind of different looking as you kind of go across it. Now, what we know about the interior of our planet really all comes from earthquakes. Like I said, we have not drilled through the crust. So all that stuff inside of the earth, we're using science to figure it out based on what we know about wave properties and earthquakes and the different types of waves that they generate. So just looking at this picture right here, you can see that some of these earthquake waves are passing through the cores there, and some of them are reflecting off of it. Some of them are refracting as they go through. So that's really how we figure this out. And we'll talk a little bit more about this as we go here. Let's compare the different types of crust that we have. So in that upper part of our planet, the crust, there's what's called continental crust, and then there's what's called oceanic crust. And they have some pretty serious differences. The continental crust, as I said earlier, is thicker, but it's also quite a bit lighter than oceanic crust. Its density is only about 2.7 grams per centimeter cubed. And it's old. It's considerably old in comparison to the oceanic crust. The continental crust is up to like 4 billion or more years old. It's almost the age of the Earth itself. So we have some very, very old rock that's up here on the continental crust. It's thick, it's old, it's light, it's mostly composed of granitic type rocks. Let's compare that to the oceanic crust, which is exactly the opposite. Oceanic crust is made up of that basaltic rock. It's very dark looking. It's the stuff that's flowing out of the volcanoes in Hawaii. Its density is quite a bit higher, 3.0 grams per centimeter cubed. So this stuff is heavier. It's also much, much younger, only up to about like 180 million years or less. So comparing that to even a billion years is a drop in the bucket. Which is why when we look at plate tectonics later, we'll recognize that oceanic crust, when it runs into some continental crust, always gets forced underneath the continental crust. It's thinner, it's heavier, and it's also younger. Okay, it always gets pushed under, so it's getting recycled much, much faster than any continental crust is. As we move down from the crust, we enter into a layer known as the mantle. And the mantle runs beneath the crust up to a depth of about 2,900 kilometers. Its composition, it varies a little bit, but it's mostly of this rock known as peridotite, and it's kind of a greenish, sort of blackish looking ultramafic rock. It changes a bit more, it gets a little bit more dense at deeper depths, but it's some pretty dense stuff, the mantle. It makes up a significant part of our planet, right? Beneath the mantle lie the two cores, and we'll break this down a little bit more here in a second. The cores make up a sphere with a radius of about 3,486 kilometers, and they are composed primarily of an iron-nickel alloy. So our cores are metallic, and this is also part of the reason that we have a magnetic field on our planet and the life can exist at all. There's also a lot of radioactive stuff down there, which is generating some of the heat that runs plate tectonics. We're talking about a much higher density down here, obviously, like all that weight on top of it, forcing it together. It's very, very compact, and we're talking about nickel and iron, which are dense to begin with, right? Now let's go ahead and look through some of the layers again, kind of up near the surface of our planet. and sort of break those down a little bit more closely here. The uppermost part of Earth's surface is known as the crust, and if you continue downward from the crust, even to the uppermost part of the mantle there, sort of those two things together are called the lithosphere. So lithos meaning rock, rocky sphere. It's all rigid stuff. It's very hard. It cracks. It breaks. It's a solid. Okay, so about to 100 kilometers thick this stuff is. So the crust in sort of the uppermost part of the mantle. Now, just beneath that upper part of the mantle is this area. It's a thin area known as the asthenosphere. And this is an important area because this is the area that the plates, which are the lithosphere, are riding around on top of. And you can think of the asthenosphere sort of like a silly putty sort of a material. It's not liquid, but it's soft, kind of like a putty, and it's easily deformed, and this is the stuff that's sort of moving and dragging and pulling the plates along with it as the heat from the Earth wells up from the center up towards the surface, and that's known as the asthenosphere. Down below the asthenosphere, we enter into the lower mantle, okay, about 660 to 2,900 kilometers. This is more rigid again. The rock down there is really hot, but is still capable of flowing very gradually. So this material, I think most of the time we think of it as moving kind of upwards and along and then sinking back down. It kind of has this sort of convective sort of a flow to it that helps to move the plates around and heats up that asthenosphere layer. And down beneath that, we enter into the cores. And the cores there's two cores. There's an inner core and an outer core. So just beneath the mantle is the outer core, which, this is going to sound bizarre, is actually liquid. Okay, the outer core is liquid. The inner core behaves like a solid. Now, why is this? Because you would think, the further I get towards the center of the Earth, the more dense this stuff should be, the more weight is sitting on top of it, the more tightly packed it ought to be. It ought to be even a harder solid right as I get deeper and deeper. But what happens is at some point there's so much pressure and so much heat that you reach sort of this perfect balance where iron and nickel become liquid. So it's liquid for a while, and then just beneath that layer, the pressure is so great that even though the temperature is so high, it would be liquid, the pressure is so great that it's actually solid. So it's kind of strange, like we say, it behaves like a solid, even though it would really be a liquid, it's actually quite solid. So either way, answering the questions on It's Learning, the outer core is liquid, the inner core is solid. And it's the movement of that outer core that's made up of this metallic nickel and iron that actually generates Earth's magnetic field. It's called the dynamo effect. And by moving like that and the Earth rotating on its axis, we create this magnetic field that shoots out the two poles. That's why we have north and south and a compass works. And it also protects us from some really nasty radiation from the sun. It gives us our northern and southern lights. The aurora borealis and the australa borealis, protects us. It actually allows life to be possible. If our Earth cooled off in the core and we stopped generating a magnetic field, we'd all be toast. It'd be over with. So let's look overall at the entire Earth's structure here. Here's a nice picture of the entire Earth, and while it's kind of to scale, the part that's really not is the crust there. If we were to draw the crust really to scale, you wouldn't be able to see it. Like the thickness of a pencil line around the outer edge there is really too thick to be properly to scale. But this picture's nice because you can walk from the inside, the inner core there, out to the outer core, and then go across the lower mantle, and then the upper mantle plus the crust there. If you look at that little snapshot where it blows it up off there to the left, you get to see that whole thing. We've got the upper mantle, which is composed there of a portion that's known as the asthenosphere, which is sort of that means like weak sphere, which what the plates are riding around on. And then there's the continental crust there, there's the oceanic crust, and the little line just beneath it there is still upper mantle material that's all riding on top of that asthenosphere, right? But that's known as the lithosphere, or the hard rocky part of our planet. Now, how do we know all this stuff? How do we know the structure? Well, I hinted at it before. The answer is, of course, earthquakes. So by studying earthquakes, we found that there is a weird boundary that actually separates the crust from the mantle that's underneath of it. And this is known as the Mohoviric discontinuity boundary. And it was discovered by this guy, Mohoviric, and it's named after him. But what we noticed is that seismic waves that are passing through the Earth from earthquakes suddenly do something very different when they hit this. Their velocity actually increases really sharply just below about 50 kilometers of depth on the Earth's surface. And so we know there's a different zone down here. It's obvious. We also have a zone known as the shadow zone, which is further down. And what happens down at the shadow zone is also interesting. We notice that there's two types of waves in an earthquake. We talked about this last time. There are P waves, which stands for primary, these push-pull waves, and then there's S waves, which stands for secondary, which kind of do an up-down motion as they move. And in this zone we call the shadow zone, there is an absence of P waves in this zone from about 105 degrees to 140 degrees around the globe from the site, from the focal point of any earthquake. And now this fact can be explained very easily if the Earth contains a core that's composed of material that's unlike anything else in the mantle. Now, what would do that? Well, based on our physics understanding of these wave types and how these waves move on Earth's surface, we recognize that these P waves can travel differently than S waves can. So let's take a look here. So this picture is showing you the path that P waves versus S waves take from the epicenter of an earthquake, and it has the two cores on there in yellow. So remember that outer core, that's the one you really need to look at. That's the liquid one. Now what we know about these waves is that P waves and S waves respond very differently when they pass through a liquid environment. In effect, that S waves can't pass through a liquid, whereas P waves can pass through a liquid. So if you look at the picture there, the S waves are in red. Notice what happens when every single one of those S waves actually hits the boundary there of the outer core. They just plain stop, don't they? But the P waves, they can travel through it, and they create this funny shadow zone because they hit it, and while they go through it, they kind of refract, they get bent, just in the same way as like light passing through water gets bent. If you've ever noticed that if you're looking at fish underneath the water, they're not actually where you see them underwater. They're off at an angle to where you see them. So if you were like spearing a fish from the surface and you shot your spear right at where you saw the fish, you're going to totally miss, because that's not where the fish is, because the light's bending as it goes from the air through into the liquid. And the same thing happens with these earthquake waves. For your question there, if you're trying to answer that, the P waves can travel through liquids. They get deflected, of course, but the S waves cannot. They just are completely stopped. So there's this completely missing zone of waves there on the backside of the core. We're missing the S waves because they can't go through that liquid core. So this is really how we know about all those different boundaries on our planet. Now, looking at our composition, the early seismic data and drilling technology tell us that the continental crust is mostly made of this lighter rock. So we've drilled down into the crust a good ways, We haven't gotten through it by any means. We certainly have not drilled down to the core. And we found that the crust, the continental crust, is pretty light stuff. The oceanic crust is mostly basaltic. The mantle is a little bit more speculative, right? We've not drilled into the mantle. So how do we know what's down there in the mantle? How do we know that it's this ultramafic peridotite rock? Well, the truth is that occasionally some of this stuff actually gets to Earth's surface during volcanic eruptions. And so it's possible that we get some of this material, and we have examined it in the lab, so we have a pretty good idea of what's down there in the mantle, even though we've never drilled that far. When we talk about the core, well, now we're 100% relying on science here, because we in no way can we examine core material, right? But what we can do is we can examine the material that's in metallic meteorites that we think is pretty similar in composition to our core. So we assume here that pretty much all the planets in our solar system, the rocky planets anyway, have cores that are a nickel-iron sort of composition, because the nickel-iron meteorites are very, very common in the solar system. And if we date those, they're some of the oldest material out there. So that's probably what our core is made up of, and the facts fit, right? When we look at the earthquakes and we look at the way the waves move, the facts fit very well. So you should be able to answer all the questions on your quiz right now. Go ahead and submit that, and you are all done for the day.